lab. Congratulations, you passed the test, and we'll be working on this station here, okay? And so the purpose of the lab is to collect GPS raw data measurements, and with these measurements you will be calculating the position of the receiver's antenna, okay? And the antenna is mounted on the roof, and the cable is directed through this hole here. You see these two black thick cables, okay? It is being channeled to this desk for easy operation of our lab, okay? So these are the GPS receivers. This is the GARMIN GPS, yeah? So it's late 90s model. It has this kind of monochromatic LCD, this kind of LCD you find in your olden days game boards, okay? And it has position. Also, it has map, which longitude and latitude, you can navigate with it. Old, but it works. For the purpose of this lab, we are using it, okay? And here you have the connector to the antenna, okay? This is the GARMIN, and this is the NOVATEL receiver, model 2005. More expensive, little accurate, and more like aviation class, right? And it has these connectors, one connector to the power, two connectors to the monitors. We're only going to use one connector, and then a connector to the antenna, okay? All right, so we'll start with the GARMIN GPS. Before I connect this, who can tell us how many measurements actually we're going to make today?
Numbers of sets of data?
Yeah, so for GARMIN and for NOVATEL GPS in conjunction, how many measurements are we doing today?
We're talking like two from cold start and hot start?
Yes. Well, okay.
So it's at least two until we get the data with cold start, and until we get the data, and for some time with the hot start when we get the previous data, which is done for both GARMIN and NOVATEL, but for NOVATEL we will also have IMS.
So altogether?
So 3 different times, or generally it's 5?
For GARMIN, so cold and hot start measurement, and for NOVATEL, cold and hot start measurement, and then the IGNOS. That is, NOVATEL has 3 measurements. The IGNOS, why? To see how the IGNOS corrections affects our measurements. Okay. All right. So let me connect the GARMIN GPS. Okay. So this is the lab view for this GARMIN GPS. Here you see the current coordinates of the receiver, okay, the latitude, longitude, and altitude. Maybe we'll start the measurement, then I will discuss what we are seeing here, okay? But what I would like you to remember is that these values, this is in degrees, and the rest from the is in minutes. So you need to divide this section by 60 and add it to the degrees so that you have the whole values in degrees for easy, post-processing of your data, okay? Okay, so I'll turn on the GPS, and also I will need one person to use a stopwatch, so that so if we start a measurement, you will be observing this this information here. The time it changes here is when you have your cold start or hot start, okay? So one person should be in charge of that. Let me turn this on. Yeah, I'll let you know when to do that, because we will log the file, and then we'll start with the cold start, okay? All right. So here you can see the anemia code, right? So this is the anemia code. Please remember that the frequency of the data login, it's 1 Hz. So you can see these are the codes that you are seeing, the anemia codes that you're seeing here. So frequency of the data login is 1 Hz, and you are interested in the GGA and the GSA messages for your reporting and post-processing of the data. Okay, this is just a visualization here. You will be having this data in the saved in a file. I hope you have a pen drive to collect the data. Anybody has a pen drive? Okay. All right, so we will log in the file for the first measurement, which is the cold start. Okay, and I'll let you know when to do that. I'll save, create a folder. Today is 11th, April 2025. Okay, I'll save this one as a GARMIN code. Okay, so we're using this antenna here. I will be connecting the antenna, and then I'll click save, and I'll ask you to start the stopwatch, and then when you see changes here, that is when the cold start has happened. Okay, so start. All right, so we'll wait for the measurement to kick off. So here you'll be seeing the signal strengths, like signal strength and the quality. So here is the number of the satellites, okay, and here is the signal strength. Now it is one satellite being in track and it's in gray. It's not being used for the solution. When it turns blue, these will be the satellites that are being used for the position fix. Okay. So this is now it is collecting the almanac data and setting up for the position fix. Here you will be seeing the azimuths, okay, azimuths and elevation. This is the azimuth and elevation window. You will be seeing the satellites. So let's say that you're on the center of this circle, and this is your horizon. You're seeing the satellites in the sky, the ones that are visible. Okay, you'll be seeing them here. Okay, and this is just the journey. You'll be seeing the graphical journey of the position here. So this side is not really important for us. We're interested in seeing the altitude here, how it will be fluctuating, and then you will have your conclusions, the accuracy or the
And this is the first satellite, right?
yeah, so you have to observe here when it changes. That's when you click stop, and then this will be our time of the cold start. So yeah, you will see the satellite in the sky. We will be observing this area here to see the time of this cold start. How many minutes at this moment?
2 minutes 12 seconds.
Okay, so now,
Okay.
did you stop it? It's still ready.
Yeah, I took the.
Okay, all right. So that's about two minutes. Yeah. So you have that in mind. So when we do the hot start, that you will do your you will have your conclusions, the difference between the cold start and the hot start. So at this moment, pretty much 132 meters. Okay, for this kind of old receiver, it's not bad having this value close to the real altitude of the elevation of the antenna, 135 meters.
Where is the antenna?
It's mounted on the roof above sea level. Okay.
Huh?
All right, and then what are we seeing here? So these are the satellites here. The ones in blue are the satellite being used for the solutions. The higher the value of the signals, the better. But these ones in blue, as long as it's in blue, it is being used for the localization. Okay, you have the PRN, the pseudo random number, which is the unique number, identifier number for a satellite. And you have the azimuth, the direction of the satellite, and then the elevation of the satellite. Okay. Now, before it was 131, now it's getting to pretty much close to the real elevation of the antenna. Okay. What could be the assumptions at this moment between this GPS receiver and the GPS receiver from your phone?
The differences?
Yeah, what is the conclusions or assumption you may have in your mind, imagine the GPS that you have in your phone and this GPS here?
We don't usually have cold start in phones. Usually there's some data saved and then we get the hot start. We don't have to wait a couple of minutes.
And why is that?
Because it's faster and usually
If it's faster, but why is it faster?
it uses triangulation from GSMs.
And what else? All right, so you have also the GLONASS data information in your phone, and also Bluetooth and Wi-Fi. So with that, it is faster on your phone for easier localization. But here it's only using GSM system. DOP, deletion of precision. Okay, here is the position accuracy is 2, and the horizontal DOP is 1. You can come closer to see it. The vertical accuracy is 1.7. Okay, and that's that. But we'll concentrate on that more when we do the NOVATEL IGNOS to see how this IGNOS corrections affects measurement. So DOP, deletion of precision, is a metric number. It's a metric number used to measure the quality of the GPS position estimate. So the value close to 1 is a better position accuracy, while value above 5 is a poor position accuracy due to poor satellite geometry. So that's the definition of the DOP. So bear that in mind. If you're having values 1, 2, up to close to 1 is the best value, and above 5 is a poor position accuracy. Okay, and we are having pretty much close the altitude 135, which is good. Okay, and the coast start started about 2 minutes. So I think it's enough data collected. I will save this one, and then we'll do the hot start. So the hot start, I will disconnect the antenna. Okay, and please, if I disconnect the antenna, measure, calculate 1 minute. Let's say you are inside the tunnel or in the mountain, you're losing the signal. Okay, and then we'll connect back the antenna, and then we'll log a file for the hot start, and then we'll see the difference. No, not yet. When I disconnect the antenna.
Okay.
Okay, now. Okay, 1 minute, and we'll log a file, and then we'll call it GARMIN hot. And when I connect this and save, I'll ask you to observe here one more time. So you have to be fast on this one. Sometimes it is faster.
Okay.
Sometimes it is faster, so you can observe the difference.
Okay.
Moment.
Okay.
Not yet. Okay, you observe here. Okay, now. See, it already changed, like seconds.
Yeah.
So it has already data already saved. It doesn't need to do the localization fix, so it's pretty much faster, like 3 seconds, and the coast start was about 2 minutes. continue for 4 minutes. You don't need to stop it. Continue for 4 minutes. Okay, so pretty much it's still the same information that you see in here. You'll be observing here how the altitude is fluctuating. Do you know why it is this altitude is fluctuating? Like our real altitude is 135, but here it is fluctuating between 131 and 137. Anybody knows why this altitude is fluctuating?
Atmosphere errors.
So atmospheric interferences might interfere with your measurement. So let's say we're in this room here. If you're outside, the tall buildings or tall trees may interfere with your measurement. That's why you're having this fluctuations. Also, you can have GPS errors that will affect these values.
Can I ask something?
Yes.
Why it turned to gray?
Yeah, the gray color is the satellite that's not being in use.
Oh, okay.
Okay, and the higher these values here, the signal, the better for the.
So the numbers are signals.
Yeah, the numbers are signals, but this ones here is the satellite number.
Oh, okay.
But these ones are the signal strengths. Okay. This is the GARMIN measurements. So we'll move to NOVATEL measurement. So the same process, I'll let you know when we are doing the NOVATEL measurement. The same process, you calculate the time of the cold start and the hot start. We're just going to be antenna for 1 minute. So keep track of the stopwatch. So here you see the journey of the position, and here we're interested in the coordinates. So you have the latitude, longitude, and the elevation. Okay, and also you will be monitoring the solution type here. So it does change to single and to SBS satellite-based augmentation system, the IGNOS one. So when it's SBS, that's when the IGNOS is being used. But at this moment, I'm going to turn off the IGNOS so that we do only the code and hot start measurements. And after that, I'll enable the IGNOS so that we'll see the IGNOS correction measurement effect. And now I will set up the log files here, and we'll go to today's folder, and then I'll name this NOVATEL code. Okay. Okay, I'll connect this antenna. So be ready. Moment. So you'll be observing here, okay? When this changes, the time of the code starts.
Should I stop?
Not yet. Moment. And start. So you'll be seeing the satellite in the sky here, and here you'll be seeing the number of the satellite being tracked and the number of the satellite being used in the solution. here you'll be seeing the signal strengths, okay? And here will be the DPO values, okay? So this time we'll be monitoring these values here, okay? Maybe from after we do the hot start, remember the values here, and when we enable the IGNOS, you can then compare the previous value that you have with the one for IGNOS. Okay. Just measuring, okay. How many minutes do we have at this moment? Did you start?
Yeah.
Oh, okay.
Well, you need 30 seconds.
Okay, it is something that's working.
Should it be faster?
This is cold start. This is cold start. So, yeah, NOVATEL pretty much is a little accurate, but sometimes it can have a delay. Okay, and in the GARMIN is doing the localization. Not even, it doesn't care if the data is correct or not, and it gives you the value. But here, it's a little accurate. Even if you have your cold start first and you disconnect the antenna and connect the hot start, sometimes it's also a delay than the GARMIN because it wants to collect a correct data to show you. Oh, okay. So like 30 minutes.
Right, so we can see on the screen here that we have 10 satellites being tracked, and also it is 10 satellites being used for the solution. Now it has changed. We now have 9 satellites, 9 satellites being used for the solution and 9 being tracked. Okay, and the solution type on the left hand side is single, which means that we're not using SBS correction system here at the moment. Okay, and the altitude here is 136 meters. Okay, pretty much close to the real elevation of the antenna, which is 135 meters. And the DOPs we have here is close to 1, which is a good accuracy. Okay, so the horizontal DOP is 0.9, the position DOP is 1.6, the vertical DOP is 1.2, the time DOP is 0.7, and geometry DOP is 1.8. It's close to 1, which is a good metric value if it comes to DOP, dilution of precision. Okay, and we'll continue the measurement and we'll collect more data for post-processing.
And I remember the horizontal accuracy was 1.2 when I was calling. Now it's 0.8.
So there is error? Or? No. Like what
No, the value, DOP, dilution of precision, the value close to 1 is a better position accuracy.
Okay.
Yeah. Above 5 is a poor position accuracy due to poor satellite geometry. Yeah. How many minutes you have?
Almost 2 more seconds.
Okay, so we'll save this one and then disconnect the antenna. You measure 1 minute, and we'll log the file for hot start.
1 minute.
1 minute, okay? I will save this. like how many
30 seconds.
So, and the altitude is pretty much close to the real value. 130, it was 134 before, now it's 136, it's fluctuating. And we are having 10 satellites and 9 of them being used for the solution. Okay, how many minutes?
Almost 4, not yet, but 1 second more, 2, 4.
Okay, I think this is enough. And now we are not disconnecting the antenna. I will enable the IGNOS, and then we'll observe this solution type here. When it changes to SBS, that's when the IGNOS is being used. You see this satellite's different shape, hexagonal. That's the IGNOS satellite.
Sorry, what was N2P?
Where?
Here.
This is the frequency.
Oh, okay.
It's L1 and L2. Four more minutes, okay? It's SBS now, okay? That's
So we can see the circular plot displays the satellite in view relative to the GPS receiver, and the concentric circles, that is the outer circle, represent the satellite elevation from the horizon to directly overhead, that is the center, and the azimuth directions is marked around the plot, north, east, southwest, indicating the satellite's directions. You can see the green icons are the satellites labeled with their unique numbers, pseudo random number, and it's visualized based on its position in the sky. The number of satellite tracked is 9, and the number of satellite used for the solution is 9, as you can see. Okay, and on the coordinates and solution information, bottom left, we can see the current geographic location of the receiver, latitude and longitude, and currently the height is 136 meters. Okay, that is 136 meters above mean sea level, which is close to the real elevation of the antenna, 135 meters. The solution type, bottom left, indicates how the position was calculated, which is SBS, satellite-based augmentation system, which is used for correction and improved accuracy. We can see the gray shaped hexagon indicating the SBS satellite. The dilutional precision, DOP, top right, as we can see, are close to value 1. DOP is the measure of the geographic quality of satellite positioning, indicating how satellites positions impact the accuracy of a GPS position fix, and a lower DOP value close to 1 signifies better positioning accuracy, while a higher DOP above 5 suggests that the calculation position may be less accurate due to poor satellite geometry. So here the HDOP measures horizontal accuracy, the vertical DOP measures the vertical accuracy, and the PDOP, position dilution of precision, combines HDOP and VDOP for overall 3D accuracy. And the GDOP, geometric dilution of precision, includes timing and geometry effects on accuracy. The signal strength graph, bottom right, displays individual satellite signal strengths for each satellite tracked, And in conclusion, the NOVATEL GPS with its implemented augmentation system (SBS) did well in improving the accuracy of the GPS receiver compared to the single mode solution in relation to the DPO values. The altitude obtained during the measurement is close to the value of the antenna real elevation. And this will be the conclusion of our experiment. Okay, and I will say bye bye to you today and see you next time.